Today we are going to continue in chapter 2 where we're talking about strain, in other words, changes in length, because we're specifically talking about normal strain. And today we're going to cover two sections, section 2.2, which is something called statically indeterminate problems, and then we're going to talk about section 2.3, which talks about expansion and contraction due to changes in temperature. So to begin, let's come over here to the document camera, and we'll start talking about what do we mean. We'll do a definition first. What do we mean by the idea or the phrase statically indeterminate problems? Okay. So statically indeterminate means that you cannot analyze these based on an analysis of forces. So in other words, the methods of statics are not sufficient to provide us with the means of evaluating certain types of problems. And so what we need to do is to use strain also. Okay. Now, an example of a problem like this would be if you have a column, or the way that they have this problem drawn, which is example 2.3, is a pinned structural member to which you apply a load P at the center of gravity at some distance L1 from the top pin and some distance L2 from the bottom pin. So in other words, L1 plus L2 equals the total length of my structural member. All right, now what we can do if we do statics, we say summation forces y equals 0, and we say negative P, and we know that we're going to have some sort of a reaction here, which we could call the reaction at A, plus the reaction at A. And since we don't know the direction, we'll call this positive as well. Reaction at B equals 0. Or we could say that the reaction at A plus the reaction at B is equal to P, which is that applied load. Now, while that's true, there is nothing in statics that's going to be able to help us solve for what the reaction at A is and what the reaction at B is. Because we have one equation, two unknowns, everything is collinear, so we can't use moments, and there's nothing going on in the x direction at all. So we are totally stuck at this point. So enter the analysis method that we just used, analysis of deformation. What that means for us is this. First of all, because this is pinned at the top and the bottom, we know that the total change in length is going to be equal to what? Sorry? Do it again. No. If it's pinned here and it's pinned here, how much can it actually move? None, right? Yeah. So the total is equal to 0. Now, because we're pulling on it here, we may get a del in L1, right? And we may get a del in L2, but the sum of those two things is going to be equal to 0. And using this idea and knowing what those values are, and relating it back to this, we're going to be able to solve this equation. So the method that we use is to once again do a cutaway where I cut here, okay? And then I will cut again here. And what I can see is that on the top cut in L1, if this is the reaction at A, and remember, if I draw it up here, I want to draw it up here as well. I want to be consistent with that. I know that I'm going to have some reactive force here, which is also going to be RA prime, and that I have this drawn in tension. So I can say, I know that in general, a del is equal to a PL over AE, right? So here in L1, my P force is RA My length is L1. The cross-sectional area and the modulus of elasticity are just whatever they are. And then if I cut down here in L2, I have P pulling down on it and R sub B pushing up on it the way I drew. I'm sorry, I should put this down here. This is my P. And then I'm going to call this my reaction prime in that structural member, in that part of the structural member. So if I do the summation of forces Y in L2, I get that P, which is negative, plus RB, and the way I have this one drawn, minus my overall reaction, which I'll just call R prime, is equal to 0. Okay? Or I can say that my reaction here is equal to minus P plus RB. Now, the only thing that's interesting here is I don't really want, you know what, let me do this a little, I want to redo this if you don't mind, because I'm getting a little bit confusing here, getting into the weeds a little bit too much. So I'm just going to eliminate this, I'm going to redraw it, and then we're going to do this a little bit differently. Okay? Like that? Okay. So I'm going to redraw this. Okay, I'm going to redraw L2, the lower half. And so what I have right here is P. And here I have RB, don't I? Okay? And between these two, I have them drawn. I'm going to have some reactive force here, which I'm just going to call R in L2. Okay, and I know that those three things at my cutaway are going to have to equal 0. Okay, so what that means for me is if I draw a summation forces in L2 equal in the y direction equals 0, I'm going to get R sub B minus P plus RL2, the way I have it drawn, is equal to 0. Or I can say RL2 is equal to P minus R sub B. Okay? Now, if I look at my original equation right here, all right, I can see that R sub B, since, let's do this, since R sub A plus R sub B equals P, I really don't want this variable because I already have an R sub A in my first equation. So since R sub A, I want to substitute this, so I can say R sub B equals P minus R sub A. So I can then say that R sub L2 is equal to P minus P minus a negative R sub A, or R sub L2 is equal to R sub A. Okay, now, so when I do my free body diagram here, I can then say that R sub L2, which is R sub A, see, I'm going to get in the weeds again, and I hate to do this because we're not going to come out with what I hope to come out with here. So let me think about how I want to approach this. See, this is where do I want to really just keep those in A's and B's? Boy. All right, I want to go back to my original free body diagram here. So this is where I'm just getting into the weeds here, and I'm undoing some of my own work. This is RA, This is RB, and this is P. So once again, R sub A minus P. I guess I want to change this direction. It doesn't really matter. We work the same way either way. But I get that R sub A minus R sub B equals P. All right, now if I cut here in L1, the only thing I have is R sub A. So the del in L1 is R sub A L1 over AE. Okay, and the del in L2, if I cut it here, is only going to have R sub B. Okay, there we go. It's a L2 over AE. And then I have these two equations, and I know that the sum of these two is going to have to equal 0. Now, I need to use this equation because I have two equations and two unknowns. I'm assuming at this point that P is known. So what I could say is that R sub A is equal to P plus R sub B. That'll work. And then I could say here P plus RB times L1 over AE plus RB L2 over AE. These two things added together equals 0. So what the answer is, if P is known, you can see then that my only unknown is R sub B. So I can solve for R sub B. And then, based on my equation of statics, I can solve for R sub A. And then I can use each individual, one or the other, to see how much the top elongates and how much the bottom contracts. Because the total of those two things is going to equal 0. Okay? So let's do a problem with some numbers in it so that you can see how this works. And I will not get down in the weeds on this one. Let's take a look at problem 2.41, okay, in your textbook. We're going to use the same method. You sum the forces, this time in the x direction, and then you sum the total deflections to get your second equation in order to solve for the entire thing. Okay, 2.41. Looks like this. We have a rod made out of steel welded to a rod made out of brass. And it's constrained on both ends. We have a force here at point B and a force here at point D. And we are given those magnitudes. And what we're told is two cylindrical rods, one of steel and the other of brass, are joined at C and restrained by rigid supports. For the loading shown and known these values of modulus of elasticity, determine the reaction at A and E and the deflection at point C. Okay, so what we want to do here, this is my reaction at E. And then we can see, this is, so the first thing I would take a look at is, I generally draw things positive, but do you see if we apply these two loads that R sub B has to be pushing back? In other words, we have two loads pushing to the right, so this has to be pushing to the left. So I feel very confident with that. The other thing is that we know that the reaction at A is going to be pulling because these two loads are pulling against it. The other thing we need to know here is that the total deflection is equal to 0. Now, sort of the analysis part of this that we need to be aware of is we have two different rods, so we know that we're going to have a del for this rod and a del for this rod. But the del in this part prior to force B, the force applied at B, is going to be different than the one here and here and here. So in other words, we have 4 cutaways that we need to do for this composite rod. In other words, we need to do the del from A to B and the del from B to C and the del from C to D and the del from D to E And we know that all 4 of those will add up to 0. All right, so from A to B, let's just start here. And the only variable, I don't want to put R sub E in my equation except for the summation of forces x equals 0. I'm going to be true to my sign convention. I have a negative RA plus the force applied at B, which I'm told is 60 kilonewtons, plus the force at D, which is 40 kilonewtons, minus R sub E, and all of those equal 0. So when I add these together, I get 100 kilonewtons equals R sub A plus R sub E. But once again, this is statically indeterminate because I have one equation and 2 unknowns. So I have to use the method of deflections in order to get my second equation. Now the place where I got down into the weeds here was I was trying to use R sub A and R sub E in the same equation, and you can do that, but it's a lot less confusing if you just do your cutaways from one side or the other, so that the only unknown force that I put in my deflection equations is either R sub A or R sub E. So I'm going to just start from the left, cut on the right every single time, okay? And that'll keep me from getting too many variables that I have to substitute back in, okay? So let's take a look at this. We know that del is always equal to, not always, but when we're talking about forces, it's PL over AE. So if I do a cutaway here between A and B, my force is going to be R sub A. And it's in tension, so that's positive. R sub A times the length from A to B over the area of that rod, AC, times E of AC. There's my first. Now, if I do a cutaway here, I have R sub A negative and this force at B positive. So for this second section from B to C, I don't really know if my reaction is positive or negative, but I'm going to call it positive just because, I don't know, because I want to. So I'm going to do a, let me see, I'm going to do a cutaway here. Let's do this. This is the cutaway on A to B, which is summation forces x equals 0, negative RA plus just negative RA, and then I have this responsive force plus RA prime equals 0, so RA prime is equal to R sub A, which is what I use here. In BC, I have R sub A, and I have this 60 kilonewton force. And then I have some reactive force, which I'm going to call positive. I really don't know if this is positive or negative, but we're going to find out. So whatever this reactive force is, I'm going to then say summation forces x equals 0, negative R sub A plus 60 plus R prime is equal to 0. So I can say then that R prime equals R sub A minus 60. So for part BC, that's what I'm going to use. R sub A minus 60 kilonewtons times the length from B to C over the area from A to C times the modulus of elasticity from E to C. So now I have my deflection of the entire rod A to C. Once I compute R sub A, I can then compute the deflection of C. In other words, this point C is going to move over, I think, to the right, and this part is going to shrink by that corresponding amount. So these first two terms are going to get the second part of the equation, but I have to find out what R sub A is first. Okay, so now let's look at C to D. Let's look at my cutaway at C to D. Well, my forces are the same. I don't have another force here. So if I cut away here between C and D, I'm drawing this like that. Okay, I still have R sub A, and I still have the 60 kilonewton force. Can you even see that? No, there we go. And then I've drawn this one positive. It's the same reaction, so I want to draw that the same way. And so, same equation, summation forces x equals 0, negative R sub A plus 60 plus r prime equals 0. R prime then equals 60 minus r sub a. So in other words, the force in this cutaway and this cutaway are the same. They're both r sub a minus 60. Only now I don't have the length from B to C. I have the length from C to D over the area. Cross-sectional area from C to E is exactly the same, and so is the modulus of elasticity. All right, now in my last section, if I cut away here, we know that that's going to be equal to the reaction at E. However, if I'm going to stay true to myself and cut that way, I'm just going to call that r sub prime. And I'm going to say over here, I have r sub a, and then I have 60 and 40. Okay, so when I do the summation of forces in the x direction from D to E, I get negative r sub a plus 100 minus r prime equals 0, or r prime is equal to 100 minus r sub a. And that's what goes in my last chunk of the equation. So this is 100 minus r sub a times the length from D to E over the area from D to E times the modulus of elasticity in DE. And all four of these terms adds up to be 0 because the actual deflection total of that bar is equal to 0. All right, now the good news about this equation, we only have a single unknown, which is r sub a. And if it were different than that, we wouldn't be able to solve this problem. But they're structured so that with the deflection analysis, you can also find r sub a, or one unknown. Then you can go back to your original statics equation and solve for r sub e, because you know that they sum up, or the difference, the sum or the difference of them is that value of the force applied plus the force applied. All right, so let's take a look here and put in some numbers. We get the r for A, the reaction at A, times the length of AB, which is 180 millimeters. So I'm going to call that 0.18 meters. Now A and E for these first two terms are the same, so I'm just going to factor those out. And so here I get r sub A minus 60 times the length from B to C, which is 120 millimeters, or 0.12 meters. That entire, those two numerators go over the area of C. Let's go ahead and compute that. We're told that it's a 40, A to C is 40 millimeters in diameter. So we know that the area from A to C is equal to pi d squared over 4, or pi times 40 millimeters, which is 0.04 meters, quantity squared over 4. Okay, and let's do that calculation. 0.04 squared times pi divided by 4 equals, so the area of AC is equal to 1.25 times 10 to the minus third meters squared. Okay. And let's go ahead and compute the area of CD or CE since we're here. Once again, it's pi times the diameter squared. The diameter this time is 30 millimeters, so it's 0.03 meters, quantity squared over 4. And so the area of CE is 0.03 squared times pi divided by 4. So this is, see, that's wrong. I got something wrong here. 0.04 squared times 3.1416 divided by 4. Okay, that answer is correct. 0.03 squared times 3.1416 equals, there we go, divided by 4 equals. That number is 7.07 times 10 to the minus 4 meters squared. When I first did this calculation, I ended up with this number being larger than this number, which is not possible for having a smaller diameter, so I had to go back and recompute that. All right, so then finishing up this, putting in my numbers, the area from B to C then is 1.25 times 10 to the minus 3 meters to the third, meters squared, excuse me, times the modulus of elasticity for steel, which is 200 gigapascals, which is 10 to the 9th, Newton per meter squared, okay? And then added to that are my second two terms, RA minus 60 times the length of CD, which is 100 millimeters, 0.1 meter, plus this term, 100 minus R sub A times LDE, which is also 0.1. Oh, I could factor that out too. But that's okay, we're already here. Times the area, which is, or divided by the area, 7.07 times 10 to the minus 4 meters squared, times the modulus of elasticity for brass, which is given as 105 times 10 to the 9th, because it's gigapascal Newton per meter squared. And all of those things added together equals 0. Now, I'm going to have you guys, I'm going to break this down for you. I'm not going to work through the algebra or the arithmetic. I'll work through the algebra. But let's take a look at what we have for units. Meters squared cancel. My reaction at A and this, those are in kilonewtons, so I really need to multiply. If I have that in newtons, I need to multiply that by 10 to the third to get newtons, right? This will be in newtons, so if I do 10 to the third, all of my forces will cancel out. And what I have then is a meter. So is meter a good number for a deflection? We're talking about expansion or contraction, so it's a good unit, isn't it? So it should be a very tiny, tiny number. But anyway, so what we want to do then first is to solve for R sub A, but I was just checking to make sure that I had everything all together here. So if we want to separate out R sub A, the first thing that we need to do is we could find the numeric value of each of these numerators, and then we're going to need to distribute this 0.12 to get my R sub A separated out, okay? So for my first two terms, I get 0.18 R sub A, and then when I multiply this is going to be plus 0.12 R sub A minus 60 times 0.12, which is 7.2. So that's minus just the value 7.2 all over this denominator, 1.25 times 10 to the negative third times 200 times 10 to the 9th gives me a value of 250 times 10 to the 6th. Okay? Add to that, here I need to distribute this. This is going to be 0.1 R sub A. And then when I multiply these two, I'm going to get minus 6 is the numeric value here. Then when I multiply 0.1 times 100, I get 10. So this is plus 10 minus 0.1 R sub A equals, over this sum, or over the product here, 7.07 times 10 to the minus 4th times 105 times 10 to the 9th is 427.35, and that's going to be 4 times 10 to the 5th, okay, equals 0. Okay, now if you look at this second term, I have 0.1 R sub A minus 0.1 R sub A. So the R sub A's here go away. They cancel out. So what I'm left with, if I add these two together, I get 0.3 times R sub A minus 7.2 all over 0.250 times 10 to the 6th plus, this is negative 6 plus 10, which is 4, over 427.35 times 10 to the minus 5 equals 0. Can I solve this equation for r sub a? Absolutely. I can find a numeric value here, bring it over to this side of the equation. I could also just get rid of this numerator by taking it and dividing it through. So I'm going to say 0.3 divided by, there's not a point there, that should be just 250. That was just me writing stuff. Divided by 250, and that's times 10 to the 6th. So if I take 0.3 and divide by this, I get 0.0012 times 10 to the minus 6 r sub a minus 7.2 divided by that. Same thing, 250 is 0.0288 times 10 to the minus 6, and that's a constant. And then I take this number plus 4 divided by 427.35. That's times 10 to the 5th. Yeah. I had minus 5th there, but it's not, it's 5th. So this would be, this divided by that is 0.00936 times 10 to the minus 5th. Those three things equal 0. Okay, so then what you can see is that we have a number multiplied by r sub a, and I can bring these two over to the other side. So I got to, okay, so I have 0.0288 plus 0.00936, and this is a wee little number, 1, 2, 3, 4, 5, 6, 7. And it's going to be, this one's bigger, so that's a negative 1.22 times 10 to the negative 7th. When I bring it over here, equals 0.0012 times 10 to the minus 6 r sub a. That means that r sub a is equal to negative 1.22 times 10 to the minus 7th over 0.0012 times 10 to the minus 6th, and that's going to be in newtons because I got rid of my kilonewtons. So I get that divided by 0.0012 is, yeah, that's a wee little number. This should be a positive, comes up here. Okay, so it's not that small. 1.22 divided by 0.0012. That value is 101, 1,000, and then so we've got 10 to the minus, so that becomes 10 to the minus 1, and that number then is 1016.7 times 10 to the minus 1 newtons, or if I bring that over, 101.7 newtons, or 0.1 kilonewton. Okay. Now, the one thing I want to point out, this is the correct method for solving these types of equations. Now, I found out what my r sub a is. I can then plug it into this equation to solve for r sub e, because they total to 100 kilonewtons. And then I can go back and I can solve for this deflection just using these first two terms of the equation. Now, the thing I want to point out, there's a lot of arithmetic in this, and there's a lot of chances to make mistakes. The setup is really the thing. And when you do your homework, I'd like you, and first of all, I've got an arithmetic mistake in here. It's extremely common that you have to work these things a couple of different times to make sure that you've got your powers of 10 correct, make sure that you have everything arithmetically correct. But the big thing when you're doing an exam is the setup, okay? Because I really don't expect you to be able to chug this out in 15 minutes. It just ain't going to happen. Well, maybe it will. Maybe you guys are good at that, but often it doesn't happen that way. So the setup is the big deal. So the things that I'd like you to take away for today are that the total deflection is equal to 0 in this case. Now there are some problems where there's a total deflection that's not equal to 0, such as if you look at problem 258, where we have, I'm just going to ask you this question for 258, where we have something like this, and if we have a gap right here, that gap, that's going to be our del total, isn't it, if this thing expands clear to the end. This would be due to temperature expansion, which we also didn't get to today. So we will get to that on Monday. But basically, whatever the allowed deflection by the geometry is the del total, or the del total would be less than that. Okay? So you can find a del total, and then you can go back and work that part of the problem with the statically indeterminate or analysis by deflection. Okay. At this point, do you have any questions? What I'd like you to do for your homework tonight, and I will post the one from the first ones from chapter 2, but go back and work this. My setup is correct. I would like you to go through my arithmetic and fix the problem because it's not 100% correct, and I would like to see it 100% correct. So fix the arithmetic on this, and then we'll talk about it on Monday. All right? All right. You guys have a great weekend. Here we go.